Okay, so you should all be able to see skills session 8 now. So I think at the start of the tutorial on Monday, not the thing that was cancelled, but the tutorial went ahead. It accidentally said skills session 8, but that wasn't a skills session, just to clarify. So this new document is on Keats now as well, if you want to download it from there. So it's more kind of revision question that touches on various parts of the syllabus. See if the pen's working yet. That's fine. So, okay, the first one is to do with the binomial model, but it's not a specific work example. It's just a general question. It says, explain how to approximate the delta and the gamma of a European or an American option under the two-step binomial tree using a finite difference approximation. So if I just draw our typical tree here, there, and there, and there, and there. Okay, well, some actually, I mean, it works in more generality, so I'll consider the possibility of a path-dependent option as well. So we have S0 there, S0U there, S0U squared, S0D, S0D squared, S0U D, S0DU, although those two payoffs are those two stock price values are the same, but the option payoffs may not be for a more path dependent one. So we denote that node by FU, that node by FD, that node by FUD. Sorry, if that's FUD. Let's do that again. FUU, FUD. This is annoying. I'm to write all this out. Okay, FDD. Yeah, so just the usual binomial tree setup. So I'm not giving you any particular option to price here, but here's the usual thing. If the stock goes up and up, the option payoff is denoted by FUU. If you go up and then down, it's denoted by FUD. If you go down and up, it's FDU, and if you go down and down, it's FDD. So the question is at time 0. So for an actual proper full question, I would give you a payoff to consider at the final time. You would compute the FUUs, FUD, FDU, and FDD. You would use the usual backward induction procedure to compute FU and FD. And remember, if it's American option, you would then compare the FU against the intrinsic value of the option. So for an American put, you would compare against maximum the strike price minus S0U, and then you would take the maximum of the original FU that you get and this value. So there's two maximums there. So if you want, you can call that FUE if you like, because that would be the European value at this, which may get replaced by the increased value of this if this value is larger than that. But even though I'm not really talking about that in this particular question. But anyway, the main point is that I should say as well, you'll need a calculator for the exam. You can ask the office what the official type of calculator you need is. Probably some Casio thing, a cheap one. So because you may have to do a numerical example in question 1 of the exam, which could include the binomial model. So if you've done a numerical example as we did, when we were looking at binomial, you would get back to your option price. So I should obviously put F0 here as well. Actually, can I get different colours? Can I? I've never used another colour before. God, that's exciting. Yeah, okay. I think I'm going to use blue from now on. Actually, yeah, it looks nice, I think. Yeah. So you would get your value of S0. So the question is, what's the delta? Well, some of you probably already. What you have to do is just redo the whole calculation by making a small change to S0. I mean, theoretically, you'd actually have to differentiate the value you get there with respect to S0, but that would be a very messy thing to do in practice. So the way you would actually do it is just to compute your I don't know. I guess, yeah, let's try the blue then. I think quite like this. So your option price F0 at S plus DS, where that's a small change in the initial stock price. And then, in fact, the better way to do it is, well, the easier way is just to compute that. So you choose a God, I can't believe it. So I don't like the look of that S0 there. So yeah, all right. Yeah, okay. So minus the original F0, when the initial start was simply S0, so that's what I mean by that expression, divided by the small change that we make to the initial stock price. So, okay, I suppose I should call it delta S0, although it looks a bit strange. But so this is what we call, I'm sure you've hopefully seen this somewhere else in your life. I mean, it's just that, I mean, the limit as ds0 tends to 0 of this is precisely the derivative that you're after. It would be f0 dash of S0, but as I said, on a computer you can't let the limit tend to S0, so you would just choose something like I would recommend a value of say 10 to the minus 5, so 0.01234 5. So you basically, it's a bit pain. Well, yeah, it might be a bit painful if you ask students. You'd have to redo the whole tree with a slightly different S0 value, and then compute the original or the new value, the option price you get minus the original value you got divided by delta S0. Now, some of you may remember that the smart way to do this is actually to instead perform a two-sided finite difference. So if I maybe write that down here, you can instead compute F0 S0 plus delta S0. The symmetric way of doing it is to perturb both ways, if you like, and then divide by twice S0. So this one is actually better, but it's more pain for you, because typically if this wasn't an exam, I'd ask you to compute the option price initially, and then you'd have to then go and also compute the option price with the stock price bumped up slightly and also the stock price bumped down slightly. So it's one of those things, if you're in the exam and you're asked to do this, I would say do it this way first, and then if you've got time later on, or if you just feel that you're easily going to have enough time before the exam, then check your answer using this method, that you haven't done something stupid. But it is it's obviously much easier to do it on a computer, but just so you're aware of how you would do that. So for the gamma, it would be the same idea. I mean, well, I know the formula. Have I forgotten how to derive the formula? So you would, yeah, let me remind. I mean, it all comes down to just how do you approximate the second derivative, the second derivative of a function. So, well, the second derivative is, of course, d by dx of f dash of x. So you basically need to perform a finite difference approximation of f dash of x, but then that itself will have a finite difference approximation. So let me remind myself, I know the final answer, but probably going to get stuck in the derivation. But let's see. Okay, so it would be well, okay, if you do it in stages, it would be f dash of x. So I'm just doing it for a general function rather, because notationally it looks a bit nicer, I think. So you'd certainly want, in general, you'd want to be thinking about, and we'll just do the one-sided one for now. Yeah, so minus f dash x by dx. But to begin with, you won't necessarily have an exact formula for f dash of whatever function you need either. So then you've got to think about how you approximate those two f dashes as well. So I'm hearing a weird noise. What is that noise? Oh, I think it was the plug, yeah. So I was just weirding me out. Hey. See? So some noise drive me insane. that's really annoying. But yeah. Yeah. So So I want to. I'll have to clear some space, or I can go insane with this as well. But so then, how do we approximate the f dash here? Well. So what would be the usual way we'd want to do that? Well, okay, I guess we can start with okay. There's different ways of doing this one, aren't there? I'm trying to remember the usual way of doing it. Yeah, maybe probably easier I look at something with Wikipedia, or I'll do the wrong one. I mean, the final formula, which probably most of you know anyway, is that the estimate of the second derivative, or the better one, is anyway to evaluate at dx minus 2 f of x plus f of x minus delta divided by 2 divided by delta x squared. Delta x is a single quantity. It's not delta times x. Delta x is just a single quantity, which we envisage as being small. So this is the answer of how you approximate the second derivative of a function you at. So f dash dash x is approximately given by this. If I can remind myself, why there's just no room. I need to make more. Okay. Let me just look at it. If we just look at this then and see what we can see in here. Well, we can see, certainly, obviously, we can see an f of x plus dx minus a single value of f of x. And, okay, it's dx squared, but if I just divide that by dx, and then from this, carrying on, because I've got no goddamn room, minus the same thing. So what should we got? It should be minus fx minus. So it should be I think minus fx minus f of x minus dx. We're just rearranging this expression into something that is more intuitive. Like, why have we got the minus 2 there? So it's just a bit fiddly, that's all. But I'm saying it's this minus this, and then the whole thing of that with a big bracket around that and a big bracket around divided by an additional delta x. So I'm claiming that this whole thing that I've written is the same as that. I think that's fine, isn't it? You just check that we have indeed got the minus 2. So we got minus fx there, minus another fx there. So that's fine. But then this is more intuitive, because we then see that this is an approximation to the first derivative at the value. And this, in fact, is also an approximation to the first derivative of x, but this is the right-sided approximation because you're bumping up the value of x, and this is the one. So there's a certain symmetry. There's a nice symmetry about this formula. So that's how you get there. I'll write that in nicely, because I think I was so busy writing out this question 3, which is quite long, that I didn't get round to, and I only added the gamma in the end. So, but basically, I mean, the moral of the story, this is the formula you would use, but in this particular case, it's not x. It would be similar to what we had here. It would be f0, the initial oxygen price, viewed as a function of the initial stock price, but you would bump up by delta S0 for some small value, 0.01, and then use this finite difference formula there. So just to say a word, so it's f of x plus a small change in x minus 2 lots of the original value of f of x plus f of x minus dx. I think the dx is missing there, divided then by dx squared. And I think there is some reason why for the second derivative dx squared computation should actually be chosen a bit larger. So I would typically choose dx to be 0.0001. If you go into the theory of this using Taylor series and that, I think that you can show what the optimal. Well, I think it's the optimal one. I mean, theoretically, the optimal value to take dx is as small as possible, but when you take into account the machine precision of computers, it's not quite as simple as that. But don't worry about that. So that's that question anyway. So essentially, I'm just saying you make a small perturbation to the initial stock price, and then you have to recompute the option price and either use, the simpler one is the delta. It's very easy to remember that one. This one's a little bit messier. So question 2, more of a kind of FMO1 type question, but it says consider a random variable x and let phi u denote its characteristic function. I'm sure we've introduced this before. Maybe I had k instead of u as the dummy variable. It doesn't matter. And remember, it's the expected value of e to the I u of x, and u here is real, and I is the usual square root of -1. So obviously I squared in -1. It says use an appropriate convergences. So by that I mean one of the standard ones that you've learned in FMO1 to show that phi is continuous in U. So to do this, we need to consider what happens as we tend to U. So a convenient way to think about that is just consider any sequence UN which tends to some U value that you're interested in proving continuity at. Then if UN tends to U, and of course we can write that as UN tends to U, then this complex exponential function is still, the exponential function is continuous, and the complex version of it is as well. So so by standard result analysis of something, if xn tends to x and f is continuous, that implies that fxn tends to f of x. So it's not something that's on the course, but okay, we're using it here. But it's an important general result. If a sequence tends to x and you then consider a continuous function, then f of xn tends to f of x as well. So in particular, so the function we'd be considering here would be the function e to the ix. So this tends to that. Okay, I've said almost surely, but I don't think we even need the almost surely there. But it's certainly true almost surely anyway. So yeah, because sorry, I did write this, didn't I? Yeah, because the function e to the ix is continuous in x. But note that we're plugging the value of x that we're plugging in is actually un capital X, where x is the random variable. So what else do we know? Well, if we consider the absolute value of e to the iux, well, from you hopefully remember this from, I don't know, when you were 17 or something, like de Moivre's formula, I think it's called. That's the meaning of e to the iux, or it can be shown that this is equal to cos of ux plus I sine ux. But then you take it. So this is the real part of this complex number e to the iux. This is the imaginary part. But the absolute value of this complex number is less than or equal to 1. Actually, sorry, it's exactly equal to 1. Yes, because of this trigonometric identity, cos squared theta plus sine squared theta equals 1. If you needed something like that in the exam, I would tell you, but I haven't always got time to write things like that in the homework questions. But I mean, it's a well-known thing. I think it comes from something to do with Pythagoras. It's called the Pythagorean identity. So although I've said less than or equal to 1, it's actually equal to 1. What I care about is that this thing is the absolute value of this e to the iux is bounded, and we've just convinced ourselves of that, assuming this is true anyway. So therefore, we can use the bounded convergence theorem to, so let me clear some space. Just to assert that, if you remember the bounded convergence theorem says, if xn is a sequence that tends to x almost surely, and xn is bounded, so we know xn is, less than or equal to some constant c, then the absolute value, the expectation of exn tends to ex. I mean, you could also use the dominated conversion, which is actually a stronger result, which does not require the boundiness. But in this case, so because of that, we've shown that the inside has almost sure convergence to ETI-UX, and this whole family of random variables on the inside is bounded. We're allowed to take this limit essentially inside the expectation and just simply get that. But okay. So I need to plug this into. Yeah, okay. Yeah, I'm moving seats actually because this plug is making a weird buzzing noise. It's driving me bonkers. But the iPad's. Okay. Okay, unless it's somebody on the call, yeah, maybe everyone mute if you haven't muted already, because there's some. I think the noise might be coming from the iPad actually, but anyway, okay, I don't know what it is, but some annoying background noise. But yeah, all right. So yes, so we finished that question because the thing on the left-hand side here is precisely phi. This thing here is phi un, and then we're considering the limits of that as un tends to u. So this shows that this is equal to phi u. I'm just rewriting what we have here. So yeah, so that's the end of that question then. So question 3 now. Again, I think I'm going to have to delete some of this stuff as well. There's just no room to think otherwise. So I should add more space in these documents. Yeah. So this question says let's MT denote the running maximum process of a Brownian motion. Just to remind you what the definition of that is. So MT, which we sometimes also call W bar T, I think, is the maximum of WS from 0 less than equal to S less than equal to T. So, and it says use a static hedging argument with standard Brownian motion starting at 0 to show that this is true. The probability that the maximum, this is the joint distribution function of the maximum of Brownian motion and the final level of the Brownian motion. By final, I mean at time t. So I claim that there's an explicit formula for this joint distribution given in terms of that and that. And why is this nice? Well, because the stuff on the right hand side only involves the probabilities of Brownian motion being less than or equal to something or greater than that, and we can easily compute these things because just in terms of the phi function. Whereas this is a much more complicated thing. This is the joint distribution of two, two separate things, related but not the same. Yeah. So this is a well-known result called the reflection principle. So the question says use this to compute the distribution, or not of the MT, but of MT itself, and explain how you could compute the conditional density of MT given WT. But I'll do a few other things in the proof as well, because this is quite well. We're already on the last question. I've also been told that I have to try and stretch the skill sets out to the full length, even though sometimes I don't want to give you too much. But so we'll use a kind of financial proof of this, which is to consider an up and out digital put option with a strike level of X and a barrier level of B. So if it helps you, usually, okay, I would consider X equals K and B equals B. But because this result isn't just a financial result. We often we typically use little x and little b just historically, but because this kind of thing was done, like many years before black shoals and stuff. So how do we go about this? Well, let's draw a picture. Usual kind of a drawing. So I'm going to barrier there. So Brian, so we're assuming it's a standard Brian, so it starts at 0. This is the time axis. Sorry. Yeah, it's a bit confusing, okay, because I've set t to be the final time. So if I want to consider early times, I should probably consider this as the s-axis instead of the t-axis. But anyway, here's the barrier level b that I'm interested in, and I also want the x level here. So, and this up and out digital put that we're considering, okay, so when does it pay? Well, if we hit the barrier, it doesn't pay. So I mean, if the brownie machine goes like that, if we hit the barrier, it doesn't pay because it's up and out. But it does pay if we don't hit the barrier and then end up below x, because x is the strike price here, but it's a digital put payoff. So remember, for a put, you have to end up below the strike price. So that's a typical trajectory that does pay, and the payoff is 1. That's the meaning of digital. So the payoff is the indicator function on. It's exactly what you see here. Actually, it's the indicator on the event that WT is less than X and the maximum also is less than B. And there's no, so we're essentially going to do option pricing as if the stock price is just simply Brownian motion is the way to think about this question. So certainly I'm going to just set the interest rate to 0 as well. Obviously, this is not the most realistic stock price process because, it can go negative, but, don't worry about that. It's just helpful to think about this in a financial way. There is an alternate way of proving it, but it takes like a whole hour to do, whereas we can do it here in like this whole question in about 15 minutes. So by the usual result, the expectation of an indicator function of something is just probability of the event. So the value of this option, we know, because there's no interest rate to anything in this question, I can get rid of that equal sign, is equal to this, is also equal to this. But then I claim that there is a semi-static hedging portfolio that can replicate this. And in fact, it's much easier to think about static hedging for Brownian motion because everything is symmetric. So I claim that a relevant static hedging portfolio for this question is to simply buy the digital put with strike X and sell the digital call with strike B plus B minus X. So what happens to this portfolio? Always with static hedging, think what happens to the portfolio if we hit the barrier at the exact moment when we hit the barrier. So if we do hit the barrier here, say, well, you own a digital put with strike of X, but you also own, we now need another line here, up here, which is the same distance away from B. Which so in total is B plus that difference, which simplifies to 2B minus it, but it's B plus B minus X. But if you're here, by the symmetry of Brownian motion, it's equally likely that from here you will end up below X at the final time T, or above the mirror image of this line, which is up here. It's just as likely you'll end up above that line as you will below that line. But because we've bought one thing here and sold the other thing, for that reason, they will both cancel each other out at the exact moment that you hit the barrier. So, I mean, for black shoals, we had a similar result, but it was much harder to prove. And I think we eventually gave a proof like a few weeks later, but it was a bit messy and fiddly. Whereas this one is almost instant. You can just so I mean, in some ways I should have taught you this one first, but I didn't know exactly sort of how much time we'd have and how things would go. But so we can see, hopefully you can see that, buying this portfolio, if you hit the barrier, it's worth 0, and that behaves the same. An up and out digital put is worth 0 if you hit the barrier. What happens if you don't hit the barrier? Well, if you don't hit the barrier, this thing pays 1 if the final stock price or the final level of the brand new motion is below X. So, but that's also the same behavior as the up and out digital put. So we can see that we've mimicked, we've artificially recreated the behavior of a digital put without actually the behavior of the up and out digital put, just simply with a digital put and selling a digital call. One thing that might, so I mean, no, this is an upper barrier in this question. A lot of our earlier questions on this kind of thing has a lower barrier, so that's one thing that can be sometimes a little bit confusing. So both portfolios are worth the same. Both, the original barrier option at times is worth the same as the portfolio that consists of the digital put and the digital call, because they both do the same thing, as long as you have the understanding that you do unwind the position at the moment you hit the barrier. So you don't want to be asleep when the barrier is hit. Of course, this isn't going to work. So therefore, because of that, we've already said that the value of the barrier option is that, but we know that the value of the other portfolio, the static hedging portfolio, is just simply given. This is the value of the digital put, and this is the value of the digital call, which we're selling. So it's this thing minus that thing. But as I said, the power of this is that these two things are easily computed. So this gives us a way to compute something quite complicated in terms of things that we know about. So I mean, if you wanted a more explicit formula for this we know is phi of x over the square root of t, and this is phi complement of 2b minus x divided by the square root of t. So we can also consider this specific, and this relates to some part of the question, or this is needed for the actual thing we asked in the question. So when it says, so we've proved this now, it then says use this to compute the distribution of MT. That's what we're going to do now. So if we set B equal X in this formula, we get the probability that MT is less than B and WT is less than B. But this is just the event is on the inside here. MT less than B is WT. Well, if MT is less than B, then WT has to be less than B, because if the maximum is less than B, how is the brand new motion going to be larger than the maximum? So we don't actually need this part there, and that just simplifies to this. So that's the key observation. Otherwise, you've just got to mindlessly plug B equals X into this formula. So, or rather, X equals B. So that becomes B, and that becomes B. So 2B minus B becomes B. So this formula simplifies to this. So this actually, I forgot to say this here. This gives us the value of what have we got? So so this gives us an explicit form for the probability that the maximum is less than B. So this is the distribution function of the maximum given by this explicit formula. But in terms of an option price, that would be, what would that be? That would be equals the expected value of the indicator function of the maximum being less than or equal to B. So what is that the price of? Well, that would be the price of a no-touch option, because you're essentially you just receive one. So know that that's simpler than the original thing that involves an up and out digital put has a strike level and a barrier level, whereas a no-touch level only has a barrier level. So we've proved something simpler from something more involved. So another nice way to think about it, if you look instead at the probability that MT is greater than B, which is the probability, which is the price of the one-touch option, one-touch. That's just one minus this, because this event and that event are the complements of each other, and when you compute that, 1 minus phi minus the phi c, this becomes 1 minus that becomes phi c of that, but you've got an additional, so you end up with 2 lots of phi c of that. So this is twice the complementary distribution function of the brand new motion itself, because you've just got simply a factor of 2 there. So if you differentiate, or alternatively, if you differentiate both sides with respect to B, the density of the maximum is given by, so because this is the complementary distribution, it's not the distribution, but you have to put the minus in front. We saw that in the very first lecture. So minus dB of this expression is minus dB of this. So you differentiate the inside, you get well, you've got a minus there, but you've also got, you're taking a derivative of phi complement, which also have a minus. So two minuses cancel each other out, and otherwise the 2 is still there. You get a 1 over square root t from the inside of that, and the phi becomes the n. So I'm using the, if you consider the phi complement function evaluated at z, d per dz of that minus d dz is the standard normal density, which is denoted by nz, and when you then plug that in, you end up with this. But we recognise this is just simply twice the density of Brownian motion itself. So, but you could ask, well, how can if Brownian motion has a density, the density integrates to 1, how can we have a density which is twice that density that still integrates to 1? Well, of course, the reason is that this density is only defined for non-negative b values. So what this density looks like is if the density of I can't remember if I did this before using a different approach, but the density of Brownian motion we know looks like that. It's just a normal density. This density is twice as high as that, but only on the right hand side. So so it's, yeah, you can call it a one-sided normal distribution, twice as high as the standard. Well, the standard normal density of Brownian motion, which it does not necessarily have variance of 1, it has a variance of t. But it's only defined for b greater than 0, of course, because mt is greater than or equal to 0. So another thing, so we can do a lot with this. If we want the joint density of wt and mt, then, well, you know, if you have a distribution function which has a density, of course, you get the density just by differentiating the distribution function. If you have a joint distribution function, as we do here, and you want the joint density, you have to just differentiate with respect to both variables. So that's a standard result, you know, from the first year or whatever. So that's what you do here. I'm not going to make you do that. It's about 5 lines of messing around, but when you do that, you eventually get to, you know, this reasonably simple formula here. So this is a joint density, but note that it's only defined on this. If we draw sort of, if we just draw this in the, so let me get some straight lines going. Let's think about what this actually looks like. Probably need another straight line. Well, the maximum is certainly positive. So let's say B is on this axis, then B and X is on this axis. We certainly know that B can never be negative, so we can forget about anything that's going on down here, you know, below. Yeah, we only care about what's going on up here. We also know that B has to be greater than or equal to X, because clearly MT is greater than or equal to WT. X can be negative. So yeah, the relevant region is this then. So it's this if X is positive, but there's also all this here as well. So this joint density is only, this formula is only correct on this funny this region that I've drawn, which includes this kind of infinite rectangle here. Maybe I'll just read all those lines because they look a bit rubbish for some reason. So you know, I'll just draw them going the other way. So yeah, as I said, the region I've shaded here, this infinite triangle plus this infinite square, if you like, is the region on which this density is defined. It doesn't make sense to define it here because that would mean that in this region B is less than X, and it certainly doesn't make sense to define it down here because down here B is less than 0. So if you want to define it in those regions, you have to just simply say that the answer is 0 and not equal to this. So I'm not too bothered about you actually, you know, computing this formula, but just to be aware that you can go from a joint density, which you have to begin with, a joint distribution function, to a joint density, which hopefully you knew anyway, but you may have forgotten. So that if you can then do things, if you want to compute the conditional density, as the question also of MT given WT, you just compute the joint density divided by the marginal density of WT of the thing that you're saying given. And if you do that and skip a few more lines, then you get to this formula here. Where it says that f of x b of is what I've computed here, and p of x I'm using to denote the density of WT. If you want, then you can also, I think this is probably an easier calculation to get from this. We can look, if we have the conditional density of W of MT given WT. You can also get the conditional distribution function of MT given WT. So I should say given WT equals X is what I'm conditioning on. So if you compute the conditional CDF of MT given that came by integrating that, so you would compute that as the, what would it be? Okay, the integral of this dB from B is X to then some other value I need to call it. I need another variable to say B1. Or if you want, but then, so you would compute that answer, but then replace the B1 by B. Alternatively, I need to replace the B there by a dummy variable and that by a dummy variable if I want to put a B there directly. And note that the integral starts at X because the lowest possible value of B is X. Again, because you always just got to remember that MT is greater than or equal to WT. So if you do that calculation, just as a point of interest, you get this quite nice simple formula for the conditional density of the distribution function, because your CDF, the distribution of MT given WT is equal to X, which, as I said, is only defined for B greater than. Let's check that it seems sensible. So what happens if X is B? So f of X given X is 1 minus e to the 0, because that would be 0, so it will in fact be 0. Yeah, so that's correct. The leftmost value of the CDF is 0. And then what about the value as b tends to infinity? Well, if b tends to infinity, this is positive, that's positive, that's positive. So the exponential will decay to 0. So f of okay, well, infinity given x is 1. So it does have the correct. Well, it's certainly a valid candidate for a distribution. Technically, I suppose you'd also need to differentiate. You'd have to also verify that this thing is increasing in B, but I won't bother doing that now. So yeah, I forgot about that. Yeah, so that's another interesting. So this is actually quite useful in Monte Carlo. It's not just a theoretical. So as I said, it gives a nice formula for the distribution function of MT given WT. So one thing it means you can do is, if you simulate WT, which I think we saw this, I mean, WT is normal around here. So remember, the way to simulate a random variable is to take FU of a standard normal, where F itself is so it's F inverse of U, where F is the distribution function of the random variable you'd be considering. In this case, WT is, of course, a normal with mean zero invariance T. So, well, we would know you'd have to compute the inverse distribution function of the normal, but you can just do that with tables in the usual way. But what it means is that if you use that method as usual to generate your WT, you can then also simulate MT given that known value WT, and let's say that known value is equal to X. You can use this formula. Well, you'd have to then also invert this formula similar to this, and then use another uniform manner to make your simulation of the maximum, given that you've already simulated W. So that's quite a nice thing to do. It's actually of use in Monte Carlo, because if you're simulating, if you're pricing a barrier option using Monte Carlo, let's see if I can use the straight line. So your brain immersion simulation, yeah, that's good. I'm going to do that again because that was fun. So yeah, that's nice, isn't it? Okay, so that was me sort of using a Monte Carlo approximation to brain immersion. Of course, in practice, I would use a much smaller. There would be a smaller step size. So the problem is, if you're simulating brain immersion on a computer, it looks a bit like this. Although you would usually, use a very, in practice, actually, you'd want a step size to be very small. Like, I mean, for your project or something, you'll want DT to be something like 0.01 or something. And let me just think. So the project. Yeah, I mean, for all three projects, at least at the moment, you will need to do Monte Carlo. So if you're, I think some of you may not be doing FMO6. You really should have done FMO6 because it really should become, you really need FMO6 for the project. So if you haven't done it, I suggest you at least get hold of the lecture notes and speak to your friends who are doing it, because you will need to do this kind of thing next summer, not now, but at some point. But so anyway, but the problem is, even if you simulate the Brownian motion like this, we don't know what did the maximum do over this. So the true theoretical Brownian motion would have been moving around like this in the interim, and from there to there. But if you're only on the computer simulating the Brownian motion in this jagged, it's only an approximation to the true Brownian motion. This formula here gives you a way of saying, well, if we know that our Brownian motion went from here to here, say, what actually was then the conditional, what's the conditional distribution of the maximum in between that range? And then so you can make an additional simulation of the maximum, and that gives you a better estimate of, if you're at the final time, if you want to compute what the maximum over the final, because you can then include those additional maximums that you've simulated to compute the final maximum of the stock price over the whole range. So because in fact, if you don't do this trick, Monte Carlo, standard dumb Monte Carlo, just using the Euler, does not converge that well, without building in this additional intelligence. But again, you can revisit that, during the project or something. But so another thing you can do is we can go the other way around and compute the conditional density of WT given MT. So I should say given MT equals B. But remember, we've shown that the density of MT is twice the normal density, so that's why I've just divided by 2pb there, but it's evaluated at b now, not x. So if you do that, and again skip a few lines of boring simplification, you end up with this formula. And okay, I mean, this is still a bit messy, but if you then let b tend to 0, you get an interesting answer that the conditional density of WT given, so well, the limit you'd be looking at here is you're looking at the density of WT given MT equals B, but I'm then taking the limit as B tends to 0. So it's quite a weird but interesting limit to take. You're conditioning on that Brownian motion never actually, if I draw it again for the last time today, in this extreme case, you're conditioning on that Brownian motion never actually makes it above the what axis is that? The y-axis, and just does this. That's the limit you're taking. So you end up with a conditional distribution here, which I think from memory is called the Rayleigh distribution or something. I think. So that's the limiting. When you let b tend to 0, this is the limiting density for WT you get, which is only defined on the. I think from memory it will look something like that. But as I said, this is this quite weird situation where you're conditioning on a Brownian motion which never goes above the axis, even though that event, the event that we're talking about, is actually has probability 0, but you can still consider this as a theoretical limit. But actually, it can also be shown, maybe counterintuitively, the probability, the probability of this happening is actually. In fact, we could probably prove, it is actually 0. So in actual fact, Brownian motion will definitely, over any small time interval 0 to epsilon, Brownian motion will definitely go positive at some point. So it's kind of an interesting theoretical, almost magical limit, which comes out because you're conditioning essentially on an event which has 0 probability. But anyway, I think that's enough. I was just trying to show you that you can do, from this original static hedging model, you can then compute a hell of a lot of other things as well. So otherwise, that's the end of that. So does anyone have any questions? And I don't have the chat in front of I'll just check the chat. Yeah, there's something similar. Yeah, I mean, I would agree that the skill session questions have been harder. That's because I meant to ask because I don't hear much from the tutors. Have the tutors actually been covering the homework questions, or do they do something else? Or maybe you don't go to their tutorials. I don't know because I haven't heard much of them recently. But they cover that, so they have been covering the homework questions. Oh, yeah, because they should talk. Well, I should probably chase them up, but yeah, so as I said, I mean, the skills session questions have been a bit harder because they don't do them and they're not specialists in financial maths like myself. So think of it as, okay, the exam would be more like, 2/3 of the questions are probably more at the level of the homework question. And then if you want to get a mark above 70, you need to be sort of, being able to answer the kind of things that are in the skills session as well. I would say the exam, you know, yeah, it's easier than a typical skills session of mine, because as I said, it was checked by quite carefully by Marcus now, and also an external examiner as well. And they gave a long list of comments about it. And in fact, I submitted the final version today. So, yeah, so there is another question is, so why the strike of the digital call? Yeah, so the easier way to remember is that it's B plus B minus X. The difference between B and X is of course B minus X, so it's that distance. But think of it as here's the mirror, and it's the mirror image of this line around the mirror that's here. So so it's always easier for me to remember it as B plus B minus X rather than just 2B minus X, even though of course they are the same. So it's just a symmetry argument. And any other questions? Yeah. Okay. Nothing else from Bruce Lee then, but so okay, so let me stop the recording there, and